For a long time, physics has had these incredibly powerful equations that describe how space-time behaves. But there's always been this deeper question nagging at us. How could space-time itself be created? Not just, what are the rules of the game, but where did the rules and the entire game board come from in the first place? Well, a recent theoretical paper proposes a really fascinating answer. It suggests that the universe we see in all its four-dimensional glory could actually emerge from the abstract rules of algebra. It's a pretty radical idea, right? It treats spacetime not as some fundamental thing, but as a property that just emerges. And this gets right to a fundamental information gap in cosmology. See, the goal here isn't just to tweak our current models. It's to offer a potential mechanism for the very origin of the fabric of reality. So the question for us is, what does this study actually demonstrate? And just as importantly, what are its limits? To get our heads around this, we'll start with the paper's core objective. Then we'll get into the methodology, this really cool idea of knitting spacetime. That's going to lead us to their key finding, a new cosmic equation. After that, we need to take a critical look at what the model doesn't prove. And finally, we'll put it all into context and wrap up with what we can confidently say about. So the paper sets out to answer a very specific, very narrow question. It's basically asking, is there a self-consistent mathematical path for a complex, multidimensional spacetime to pop out of simpler, one-dimensional pieces? To try and build this path, the researchers use a specific mathematical tool called Jordan algebras. Now, let's not get bogged down in the math here. The important thing to understand is their function. You can think of them as a very precise rulebook that says exactly how fundamental bits and pieces can interact and combine. And that really gets to the stakes of this whole thing. The big uncertainty that made this study necessary was the lack of a concrete mechanism. I mean, it's one thing to say space-time is emergent, but it's another thing entirely to propose a specific process for how that emergence, this knitting, could actually work. So, now that we get the objective, let's dig into the method itself. To make this super abstract idea a bit more tangible, the authors use a great metaphor: knitting. They basically build a theoretical model that describes how a complex fabric, our spacetime, could be woven together from much, much simpler threads. Here's how it breaks down. First, you have the threads. The model starts with these fundamental one-dimensional universes, and each one has a distinct mathematical property that the authors call a flavor. Second, you need the weaving. These 1D universes are allowed to interact through what the paper calls wormholes, which act like needles, basically gluing or knitting the threads together. And finally, you get the fabric. Through all this structured interaction, a higher dimensional spacetime emerges as a collective property of the whole system. Okay, now this next part is absolutely crucial to keep in mind. It's essential to understand that because this is a purely theoretical model, it's describing a mathematical possibility. It shows that a certain set of rules can lead to a certain outcome. It doesn't, and really can't, claim this is how our physical universe actually came to be. So, with the method and its limits clear, let's look at what the model actually found. Now here's where it gets really interesting. The model doesn't just spit out some generic spacetime. When you actually work through all the math, a specific, testable prediction emerges from the whole framework. The main finding is that this knitting process results in a modified version of the Friedmann equation, which, is one of the foundational equations we use to describe the expansion of our universe. So in other words, the model generates its very own unique law for how its emergent universe has to behave over time. This is the equation, and it's expressed as something called an algebraic curve. Here, lambda and h are just dimensional as variables. They're related to the universe's matter density and its expansion rate, the Hubble parameter. The idea is that the solution to how the universe evolves has to lie somewhere on this specific curve. And this highlights the most significant feature of that curve. It has a special, mathematically unique spot, a singular point where lambda equals 1 and h equals 1. And this isn't just some random point. It's a feature that's baked right into the structure of the equation itself. It's a natural scale that emerges directly from the algebra. So the fact that a unique equation like this pops out is a really compelling result. But it's so important that we stay rigorous and be really precise about what this study does not show. This is absolutely key to understanding its actual contribution. So let's be crystal clear here. What the model shows is a coherent, self-consistent mathematical pathway for how spacetime could emerge. But what it does not show is any physical proof. There's no experiment validating that our universe was actually formed by this knitting mechanism. Mistaking the model's mathematical elegance for physical reality would be a huge leap. Okay, so if it's not proven, why are physicists so interested in this model? Well, the reason is that it potentially offers a new way of looking at some of the biggest unsolved puzzles in cosmology. Specifically, the authors suggest their framework might shed some light on several long-standing problems. Things like the large number coincidence, the universe's strangely orderly beginning, where primordial fluctuations came from, and even the current tension in our measurements of the Hubble constant. Let's just focus on one of these for a second, the large number coincidence. This is all about the really baffling observation that several huge, seemingly unrelated numbers in cosmology, like the age of the universe in the smallest possible unit of time, or its size in the smallest possible unit of length, all happen to be around 10 to the power of 60. And here's how this new model could potentially help. That special singular point we talked about, the 1, it provides a natural, built-in mathematical scale for the universe. The authors argue that if our universe today is evolving somewhere near this special point, then these enormous ratios aren't just arbitrary coincidences anymore. They're consequences of the underlying algebra, and that really nudges our understanding from just coincidence toward actual consequence. All right, let's get to our closing resolution and answer that core question. Given what's actually in the paper, what can we responsibly say about its contribution? What we can state with confidence is this. The paper puts forward a novel and mathematically coherent framework for the origin of the universe. In this framework, spacetime isn't a fundamental building block. It's an emergent property that comes from a specific algebraic structure. The huge uncertainty that remains, of course, is whether this really elegant mathematical story has anything to do with physical reality. And that really leads to the new questions this study raises. It forces us to think, what if spacetime really is an emergent fabric? Then the fundamental laws of reality might not be written on the fabric itself, but in the rules of the weaving. And that leaves us with a final, pretty provocative thought. If spacetime is a fabric woven from one-dimensional threads, what new physics might be hiding in the weave?